Hello, everybody. Welcome back. Statics. Sorry about missing Wednesday. Everything went well. So father-in-law is doing good. They put in a new heart valve via the aorta, carotid artery. So that's crazy, down through the artery. Anyway, yeah, he's doing good. So that's great. I'm going to go over chapter 4 kind of from the beginning. And that'll give you a better feel for what's going on in chapter 4, I hope. So please go through it slowly. Pause this recording when you need to kind of process what I'm talking about and maybe work along with an example problem. That's going to be the best way to do this. So, all right. The calendar looks like this and is going to be moving quickly. Obviously, we have an exam next Wednesday, and quiz 4 will come available tomorrow and be available only tomorrow. So please don't miss it. This video this lecture should help a lot with quiz 4 and also the homeworks. So keep track of that. All right, let's look at chapter 4. So like I said in class Monday, chapter 4 goes into equilibrium, and there's 3 equations of equilibrium, and all 3 have to be true for an equilibrium state to happen. So forces in the X, forces in the Y, and some of the moments, all of those have to be equal to 0, and we set it equal to 0. So when we write the equations, we set the equations equal to 0, okay? The first step of this kind of a problem is drawing the free body diagram. So they go into free body diagrams here in chapter 4, page 63. The goal is to get a diagram that doesn't look like this anymore, but looks like this, where if there's a support, we want to pull the support out and we want to put a vector in. So the free body diagram stands alone in equilibrium and has all of this kind of information removed. So any supports are removed and any objects are removed that we can pull out. The book's going to start with a concurrent force system. That's this, right? All the forces going through one spot. And then it'll move into non-concurrent force systems. So here's another example of a free body diagram. The problem's given like this, and then we decide this is what we want to do the free body diagram of, the 10-pound weight. And so we draw it and only it. And we have a force going up. That's the rope support that's no longer there, but we have a vector in for it. And the weight of the object pointing down, right? So this is pretty straightforward. In order for the sum of the forces in the Y to be equal to 0, F would have to equal 10 pounds. Probably the easiest equilibrium problem out there, right? All right, so to get these free body diagrams, we need to know reactions and what they do. So on page 64 are all of the common reactions, okay? We just did a rope. So when we draw the free body diagram for this kind of a system, we pull the rope out, we put the vector in, it is one reaction. So these vectors that we put in, we call them reactions, okay? And I'll talk about reactions a lot, like how many reactions do we have? Those are different than external forces, right? This is an external force. Usually it's given, and we know the angle. We kind of know all about that. That's what we've been working with so far. These are going to be reactions, right? There's 2 for a pin. There's 1 for a roller. That's what this table gives us, okay? So that's what we're talking about. We have more than 3 reactions, we're in trouble because we only have 3 equations. Some forces in the X, some forces in the Y, and some a moment. Okay? All right. So let's keep going. A roller A roller allows an object to move horizontally if it's a horizontal surface. So we can pull the roller out and it gets one reaction. Rollers get one. They are always perpendicular to the surface removed. So here's the surface. Here's the surface. Perpendicular to, so it's vertical if it's horizontal, but if it's at a slope, then the reaction goes in perpendicular to that surface that was removed. So that's kind of tricky when you get rollers on slopes. Think about, oh, I'm pulling the ground away and I'm pulling the roller off and I need to put in the force perpendicular to where the ground was. All right. Smooth surfaces, they have no friction, kind of like a roller. When we pull the surface out, we put the reaction in, right? Notice the surface is gone. We want those support systems to disappear in our free body diagram where we're only left with an object and a bunch of forces on it, okay? Here's a pin, also known as a knife edge, acts the same way, or a rough surface. All of those are the same. Looks like this, we draw them as triangles. They're free pins though, free to rotate, okay? But the pin does hold it in the X and it does hold it in the Y. That's why it gets two reactions, right? Sometimes, often, we do not know which way these reactions go. We're just going to make a guess, just an assumption, okay? And our math will tell us if we're right or wrong later. All right, so a pin can look like this. A pin can look like this. This is maybe a knife edge. That's maybe a pin, okay? Two reactions, X and Y. The last one is fixed. A fixed support is like a cantilever support, a telephone pole that is concreted in the ground, something that's welded to a wall. This is like a welded fixed one, the way I've done it in red here. They can support, these kind of supports can support X, Y, and carry a moment, all three. It's the only one that can be three reactions, okay? These are called cantilevers typically. All right, so the first part of this chapter is just being able to draw the free body diagram. What's important with the free body diagram is that you take a given system and you remove all of the supports and put in the appropriate reactions, put in all the distances, and label the reactions. Very important. So the labeling system needs to be consistent with all of us. So we all have the same kind of labeling system. If this is labeled point A, then the reactions are going to be AY and AX. Okay. This is just an external load. Whatever that load was, we put it in, you know, whatever it is, 100 pounds, who knows? This is not a reaction. This is external load. The weight of this object is not a reaction. It's an external load, okay? Now, the roller, we're going to remove the ground and the roller and put the reaction in. So that is important. And we're going to name it. They named it N because it's normal to the surface removed. Well, I probably would have named it B. Not BX or BY because it's not on the X and Y, but just B or just N. That's fine. Okay. This is the free body diagram that we need before we start the problem. So in the first part of the chapter, I believe you actually start with just drawing the free body diagram. What I'm going to look for is that you have all of the information on the diagram. Distances, named reactions, named reaction, external loads, distances to that load, okay? All of that needs to be on the free body diagram. They can get complicated, right? And they can be in pieces. So this is a complicated system where we have a cylinder with some weight, we have a beam and a cable, lots of supports. So you have to decide like what are you going to draw the free body diagram of? You can draw the free body diagram of any part, the cylinder or the beam, and then sometimes we actually are going to have to draw them both. And that's what they did here. They did the system together, right? Weight, the wall was pushing here. I'll zoom back so you can see. The wall was pushing here on a rolled surface, so it got one. We did not put one in at C because they did not take it apart in this diagram. So if you do not take it apart, it does not get a reaction. It's just like part of the system. They took the cable off, a cable gets one, and a cable is always in tension, which means it points away from the point. Compression would be if it pointed into the point, but we don't have that either, okay? So we always draw cables and ropes in tension. Now I'll explain that kind of later. The weight of the beam would go in, not a reaction though, just a weight. And then the pin would get removed and we would have two. And again, we're making a guess as to which way these go, right? Something has to go up to fight that coming down and this coming down. So I'm guessing that goes up. And something's got to, the wall was probably pushing out. So it's fighting this component of this one going to the left. So that's a free body diagram of this whole system, leaving the cylinder and the beam together. Now we could take it apart. These are decisions that we will make. So maybe we just want a free body diagram of the cylinder. That would be this. The wall was pushing in. The C point was pushing up and the weight is pushing down. If this whole thing is in equilibrium, then every part is in equilibrium. That's an equilibrium, right? Or this is in equilibrium, the beam. So these free body diagrams can stand alone all by themselves and be in equilibrium. So, the drawing for that one, it's hard for me to get them both, but I'll try. Okay, that's kind of got them both, right? I'm going to kind of hide this thing because if we're just doing the analysis of the beam, it would look like this, where the cylinder was pushing perpendicular because it was round, right? A pin gets X and Y, 2, the weight of the object, and a cable gets 1 in tension. Okay, so once we get these systems, we are just going to apply the equations. This is a more challenging one because it's at an angle. So we'll start with simpler ones. All right, so let's kind of zip forward. And the first part you're going to do out of this chapter is free body diagrams. I think I gave you a couple of those where it just says, hey, sketch the free body diagram, right? That's all. You didn't have anything to calculate. Just make the drawing, right? This would be a reaction there in tension, pulling away, right? And then the cable would go away and then the pin would get removed and we'd put 2 in, right? And we guess at those and we label them AY, AX, and a lot of times I call these T for tension. Right? Boom, free body diagram, kind of done, right? Yours is going to be much prettier than that. All right. Okay, so then after we get past the whole free body diagram part, which I think is 1 through 7, it's going to actually have you start calculating some concurrent force systems like this, right? The way you do these is you start with the free body diagram. So if I'm going to pull on this with F, what horizontal force F applied to the center of the cylinder shown would be required to start to roll over the 5-inch curb. What is the reaction of the curb? The cylinder weighs 250 pounds. So this would be starting with a free body diagram, right? So let's just do it. They give you a little bit of tough ones here in the beginning because it feels like you just don't know much. But once you get the free body diagram done and then you apply the equations, it's helpful, right? So we have a 36-inch diameter and F, and it weighs 250 pounds. All right. So wish I had a bigger circle template here. I want to use something bigger. Use my cup. That'll give me, couldn't just, sketch a circle because that's going to look terrible. It might look terrible anyway. We're going to do our best to make it not look terrible. All right. So here's my cylinder, and it weighs 250 pounds. So as soon as I know that information, I'm putting it in so I don't forget. Through the geometric center, 250 pounds. Now, there was a curb, 5-inch tall curb, and so that's a round surface. So I have some kind of reaction there and some kind of reaction down here because those are both points of contact, right? So it's 5 inches down. That's important that it's 5 inches up. So I'm just going to draw a little 5 inches. Notice I am getting the curb out of there, but I'll put in this reaction and I'll call it C for curb. And I'm going to put this reaction in. This was the bottom surface, the ground. And I'll call that N for normal because it is normal to this surface that's removed. So that surface is gone. The curb is gone. And now I have all the forces in that this thing's feeling. And we're going to pull on it with F. Okay. So this problem is tricky because they want to know, well, what's the amount of force required to get this thing to move, right? So that, for me, when we pull on it, what happens to this? What happens to the cylinder about point C? It starts to rotate, right? The only way it's going to move is if it rolls up and over point C. And at that point, what happens here to N? So this is where it's really helpful to be conceptual and think about like, hey, what's happening here? Well, what's happening is N is going to 0 as this thing starts to move. It leaves the ground and no longer makes contact, right? So you got to be able to like figure out like, okay, this is statics. There's no motion, but if motion occurred, what would happen? So the sum of the moments right here would not be 0, right? Not if this thing started to go. So if I figure out like, what are the sum of the moments about this point? And if I figure out that equilibrium, then I can figure out like, oh, then I'll know like anything more than that for F and this thing starts to move. So the way to work the problem is you have to figure out moments about C. And I am going to set it equal to 0. So we are completely balanced around point C, rotation wise. Notice I'm doing moments about C, right? So I know that the thing is 18-inch radius, because I think they said it's a 36-inch diameter cylinder. Yep. So it's 18 inches from here to here. It's 5 inches from here to here, right? So that's a little bit helpful. I don't have to deal with this vector because it goes right through the point, but I do need to know like how far it is from here to here for the moment of the 250, right? I know the moment of the F is 18 minus 5, which is what, 13 inches? So I can trig this out, can't I? If I know this is 18 inches, that's the radius, right? And don't I know this distance from here to here is 13? So I should be able to get this X distance. Correct? How am I going to do it? I know I could use Pythagorean theorem. That would be X squared plus 13 squared square rooted equals 18. Is that correct? I guess if I wrote it all the way out first, maybe that would help. X squared plus 13 squared equals 18 squared. Because I know the hypotenuse, the radius is 18, right? That's everywhere. That's here, that's here, that's here, that's here. And I know this distance is my unknown x, and I know this is 13. So this squared plus this squared equals this. So I just moved this over. So now I have to, you know, that was probably the wrong move. I probably want to go with this, don't I? And say, oh, x squared equals 18 squared minus 13 squared. And then I can get rid of that and square root it. All right, so that's how to do it. X equals. Let's see if I get a number. Should be what? How big? A little less than 18, more than 13. So let's see if our math works out. $12.4498. 12.45 inches. Looks good. It's a little shorter than the 13. All right. So now I can go and say, oh, the sum of the moments about C equals F times 13 inches, and that's going to rotate negative or clockwise. And then the weight, 250, is going to be multiplied by my X dimension, 12.45 inches. And it's going to rotate the other way, plus. And I'm going to set it equal to 0. So when I do that, when I set it equal to 0, I'm finding this equilibrium state around point C, like right before it moves, ever so close before it moves. But it's not moving because I have made it static by setting the resultant of the moment equal to 0. So now I use my fancy algebra and solve for F, which is pretty easy, should be at least. And I get 239.42. 239.42 pounds. Now, it's important to understand that this is the force that you can put on this cylinder to completely make this go to 0, but there's no motion. Equilibrium means it is static, but it is at the very closest to moving, completely in balance, okay? And that means, since the question asked, but what is the reaction of the curve? The cylinder weight, blah, 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 blah. So first it wanted to know what horizontal force applied at the center of the cylinder shown is required to start the cylinder to roll. Start it to roll. This is equilibrium, but at the most balanced state. So the answer would be F would equal anything greater than 239.42 pounds. Because anything greater than this, and this thing would start to roll. Okay? So then the other question they asked was, what's the reaction at C? So at this state, what's the reaction at C? There's a couple ways to do that also. Knowing that this goes to 0, now I have 1, 2, 3 forces, and they do all, this angle should be here, and they do all go through the center. So I could draw a force triangle now that I know F, right? So you can draw the force triangle because there is no resultant. So here's F. I add them together tip to tail. Here is 250. F I know is 239, and then there is C. Right? So no resultant means it closes. 1, 2, add all 3 vectors together and it closes. So that's Sorry about that. You missed that. So here is F here. Here's the 250 down here. And then here is C coming back up. And those three forces all intersect right here at the center. They have to. That's the way rulers work. And I could get the C value, which was the next part of the problem. So I just need to square that and 250, add them together and take the square root. 240.722. So C equals 240.72 pounds. Yeah, and I would probably want to calculate the angle that it goes on. Okay, so that's a non-concurrent problem, and you're going to get more non-concurrent problems like that. Any kind of cable system that, I'm sorry, concurrent. Any kind of cable system is concurrent. These kind of problems end up concurrent because that goes through there and this ends up going through the center, right? This would be a concurrent problem if I did the analysis of the ball, this round thing, right? Because then it's in, a weight down, and a tension away. This is going to end up to be a concurrent problem. So, and then obviously any cable system is a concurrent problem. So again, we're just going to work with those equations, X and Y. This one actually started you with a moment because it was going to roll up on the curb. So that's a rotation. All right, so then it's going to move into these non-concurrent problems. And that's, I want to work one of those for you also. So I'm just going to make it up. Kind of like your quiz. This will be similar. So a lot of times we have beams, right? We work with a lot of beams in our world, especially in the beginning, because that's good, just really good practice. So I'll just give us a beam with some standard supports. These are called simple beams because they don't have that many supports. I'll put a roller here at A and the ground. So this is how the problem comes to you. And then I'll put a pin here at B and the ground, right? And then I'll put a distributed load on it. And we'll just make it a uniform distributed load, kind of right here in the middle. Right? And I'll say, oh, that's 30 pounds per foot. And this span is 5 feet. This is 3 feet. This is 3 feet. And this is 3 feet. Okay. And that's it. That's all we have. And the question is, you know, given this loading condition and this support condition, what are the loads on these supports, right? I'm going to actually change this because I don't want it to be symmetrical. So this is not to scale, but this is going to be 1 foot. Okay. All right. So now it's not, you know, it's not to scale. It's closer to this. Here, I can make that. I will leave it just like that. It's just not to scale. Okay. So step one is what? Step one is free body diagram. So free body diagram means you need to make a new drawing. And I don't care. This can be your first drawing, right? This is what's given to you in the problem. You go straight to the free body diagram. I am going to actually color code. Uh-oh, somebody took my pins. I'm going to pause because I want my pins. All right, got them. So I am going to make reactions red. Roller gets 1. Perpendicular to the ground, remove. It should be labeled AY. A pin gets 2. And I don't know which way they go, so I am going to guess. Up for AY and to the right for AX. Okay, so those are your reactions. When you remove supports, you put in reactions. The next step is if you have any distributed loads, you concentrate them. So we know how to do that now. It's going to be a concentrated load there, and it's going to be 30 times, because I need the area of this, right? 30 times 15. Is that 150? So in my free body diagram, all I put in is the 150. And I need locations of everything. So this is 3 plus 2.5. This is 5.5 feet. And then from this to this is 2.5 plus 1, 3.5 feet, right? And then this is 3 feet out here. So you have to locate everything. This is a completed free body diagram, okay? So that's step 1, including concentrating distributions. Then it's just apply the equations. So I'm going to work through all 3 equations. You'll get good at spotting the equation that you should start with. But if you don't know where to start, you should start with just summing forces. So if I sum forces in the X first, that's what the notation should look like. Summing forces in the X. That means I just look at forces in the X. How many are there? There's 1, this one. So I have, and I pointed it to the right, so it's positive, plus AX. And if there's no other forces, that's it. And you set your equations equal to 0. So that means that AX is equal to 0. That makes sense because there's no other force in the X direction, which means there's just no X forces under this loading condition, right? Loading conditions can change. So we're just looking at one loading condition. All right, next equation. Some forces in the Y, what are they? So this is where I got to pick out all the forces in the Y. I see the 150 coming down, so that's minus 150. I see the AY going up, that's plus AY. And I see the BY going up, plus BY. Sorry about that. And that's it. Just those 3, and I set it equal to 0. How many unknown in this equation? Right here, because that's how you look at it, right? This is just saying what you're doing. This kind of goes away. We can't have 2 equal signs. So 2 unknowns. 1 equation, 2 unknowns. I cannot solve it. Okay? Very common. That means I got to apply the last equation. I got to sum a moment, and this is where you get to choose. Like, choose wherever you want. You will be smart to choose where one of these unknowns is, because that drops it out of the moment equation. Because remember, moment is force times distance. It's a rotation. All right, so I'm going to do moment at A, which means AY drops out because it goes straight through point A. Does 150 create a moment? Absolutely. Right? 150 times 5.5, it's rotating that way. That looks like a negative. Does BY create a moment? Absolutely. So it's BY times this distance, which looks like 9. And it rotates the other way, which is positive. Does AX create a moment? Nope. Goes right through it, does not create moment. That's it. I've done them all. So I set it equal to 0. 1 equation, how many unknown? 1 unknown. Perfect. How do I solve it? I got to isolate it, which means move this to the other side. So it's going to turn into BY. I'll show you the long form algebra. Now it's plus because I moved it to the other side, 150 times 5.5, right? And then BY would equal 150 times 5.5 divided by 9. $91.666. and that's pounds. That's how much load's here. 91 of the 150, right? Because I know I got 150 coming down. I got 91 going up. That's what this all told me. So now AY, and I could take this and plug it into here, right? I could take this, plug it into here, and then solve for AY. But I know the sum of the forces in this Y direction has to be equal to 0. So that plus that has to equal that. Okay. Now, remember when I said I guessed at this direction? I did guess, but it was a good guess, right? Because if 150 is coming down, both of these are going to have to go up. I can see that conceptually, but if I couldn't, when you run the moment of equation, if your solution comes out positive, this is very important. And my solution did, because the negative went away when I moved it over, right? Everything is positive. If your solution comes up positive, that means you chose the correct direction. So this is tough because it does not mean that BY goes up positive. Yes, it does. That's a coincidence. What this plus means is whatever you chose in the BY is correct. In other words, if I chose BY down and this came out positive, that means that that choice was correct. So the math is telling you whether it's right or wrong. Okay? Same with the sum forces equation. If it comes out positive, then you chose the correct direction. All right. So yeah, then you plug it back in and you come up with what? AY equals, and I'll just do the math, 150 subtracted, looks like 58.33. Right? Because that plus that is going to equal that. Sum of the forces in the Y equals 0. All right, so hopefully that helps you. And again, I just made this up, right? And you're going to work some problems just like that on the homework, and then the quiz is going to be just like that. So you have a lot to do in a very short amount of time, but we have time before the exam, which is going to be chapters 1 through 4. So yeah, let me know how this went and if it makes sense. And if you have any questions, send those to me and I can make another video kind of focused on your question. Okay. All right. Hope that helps. Good luck on the homework and have a great weekend. Trying to stop the recording. All right. See you later.